Chapter 2 of your book has an interesting thing that you might not think about in terms of astronomy, but it is timekeeping, or keeping track of time by looking at the heavens. Now, this is actually how it was done since ancient times, for example. You go out and you look, and you know that if you look up, we already talked about this, you see certain things overhead at a certain amount of time, time, and later you see something else. So all you have to do is define an interval of time that corresponds to going from here to there. Okay. And so that turns out to be a reasonable sort of thing that you can imagine doing. And so they did this in the ancient world. They said, well, we can define this a particular way, and we can divide up the day into hours, an hour being related to the Earth turning. And so what they really did was they started this off by saying, well, it turns out that over the course of a year, the sun goes through 12 constellations, so why don't we define 12 hours? And so they defined 12 hours. And so the day would be 12 hours of day, 12 hours of night, and so that became 24 hours. Well, the problem with that is that in the summertime, the days are long, the nights are short. In the wintertime, it's the other way around. The days are long and the nights are short. In the ancient world, they actually had daytime hours and nighttime hours. So every day of the year, the length of an hour was slightly different than other days because it would be adjusted as needed. And so that kind of went away eventually. The Romans kind of did away with that and said, that makes more sense to have time run at one constant speed. And so that's when they went to 24 evenly spaced hours. Well, the way they used to define this was, one day is one rotation of the Earth. And so, a day is when the sun's high in the sky until it's high in the sky again, like noon to noon. That'd be a day. Except it's a little more complicated than that. Because if you look directly overhead, you see the sun. 24 hours later, Earth has made one complete rotation, but it's also moved. So directly overhead, you don't see the sun, you see empty space. You have to turn almost a degree more, 0.986 degrees, to point back at the sun. So that means a day, as you think of a day, noon to noon, is really more than one rotation of the Earth. The Earth rotates completely in just under one 24-hour period because the clock is set to noon. So the clock is actually set differently from the rotation of the Earth. And so this means that we define two different kinds of day. A solar day is how long it takes to get from noon to noon. This is the kind of time that we normally think of. A sidereal day is the actual rotation rate of the Earth, and that turns out to be 23 hours, 56 minutes, and 4.1 seconds. So just under 24 hours. So that means the day that you think of as a day is slightly more than one rotation. Well, the stars repeat every time the Earth rotates. So the stars repeat every 23 hours, 56 minutes, and 4 seconds. So that means about every 23 hours, 56 minutes. So that means that stars look like they rise 4 minutes earlier every day. So you go out at night and you see a star rising at 10 p.m., well, you go out tomorrow night, that same star will rise not at 10 p.m. but at 9:56. The next day at 9:52. The day after that, 9:48. If you see a star setting tonight at midnight, tomorrow night it sets at 11:56 p.m. and so forth. After a week, it's 28 minutes earlier, about half an hour. After 2 weeks, it's about an hour earlier. After an entire month, the stars rise and set about 2 hours earlier. So you go out tonight and you see a constellation and you're trying to do one of your observing labs and you see this constellation and it's setting tonight at 11 p.m. Well, it's going to set at 9 p.m. in a month. It's going to set at 7 p.m. in 2 months. It's going to be setting at 5 p.m. in 3 months. And so that means that eventually you're going to be noticing that this thing is set during the daytime. Likewise, you have things that rise, and they will rise at certain times, and so you watch the stars rising, and they would rise 4 minutes earlier every day. So sometimes one of the problems in the ancient world they noticed was you'd have a star and it would rise before the sun came up, and so you couldn't see it, so you would see it, but then sometimes it would rise after the sun came up. Then you never saw it. But it would rise 4 minutes earlier every day, and eventually it started rising at the same time the sun was rising. And then it was rising about 4 minutes before the sun, and then 8 minutes before the sun, and so forth. And so by counting how many days it took to go from one of those events to another of those events is how they first figured out that the year, one complete cycle of the seasons for the in other words, for the sun to get back where it was in the sky, apparently, really Earth going around the sun, was a little bit more than 365 days. And so that came from those kind of measurements here, and came from the fact that there's a difference between the solar day and the sidereal day. Solar day, that's what you normally think of as time. Sidereal day, that's the actual rotation of the Earth. So that means, that you have an interesting sort of thing. Well, in the old world, they defined the time by the sun, and noon was considered when the sun was highest in the sky. High noon was the phrase used for that. And so when the sun was highest in the sky, so it rises in the east, sets in the west, so the highest in the sky is when it's on the meridian. You remember we talked about the meridian when we discussed the horizon coordinates. So that was noon. So everybody would set their clock to noon. In fact, what would happen is in some of the big cities, clocks used to not be very accurate, and people had to reset them every day. And so they would actually have a telescope pointed up at the meridian. When the sun got close, there'd be a city, a big building downtown in the city, and they have a big spire on the top. And they'd have this big iron ball they would crank up to the top of the spire, and as soon as the sun reached the meridian, they'd throw a lever and the ball would drop. They called that a time ball. And so everybody, when they saw the ball creeping up, they knew that it was getting close to noon. When the ball dropped, it was noon, and then everybody would set their timepiece to noon. Ante-meridian is Latin. It means before noon. Or before meridian. Post-meridian means after the meridian, so that's before noon and after noon. For an ancient Roman, it meant exactly that. So if you were to have lunch with an ancient Roman, and he said, meet me at 1 o'clock for lunch, you need to be clear. 1 a.m. would be 1 hour before noon, and 1 p.m. would be 1 hour after noon. So they started timekeeping at midnight and counted down to noon, and then they counted forward in the afternoon. Eventually, in the Middle Ages, they switched that, so they just counted forward every time. Okay, but if you actually go out at noon and look up there, the sun is really not at the meridian. It's not at the highest point in the sky. That was something I discovered for my elementary school science fair project. And I didn't understand why. Why would that be the case? Well, there's several reasons for that. One is Earth's orbit is slightly elliptical. Remember, it speeds up and slows down. So that means the amount that Earth turns is not always the same, because it doesn't go the same distance every time. So that means that a solar day is sometimes a little bit longer and sometimes a little bit shorter than 24 hours. So sometimes a solar day is 24 hours and a few seconds. Sometimes it's a few seconds less. Well, you do a few seconds today and a few seconds the next day, a few seconds the next day, and after weeks of that, then you're minutes early or minutes late. And so that makes the solar timekeeping a little bit awkward. In fact, if you get a sundial, sometimes some of the better sundials come with a little chart or a table that says on such and such days you add so many minutes to what the sundial reads, and on other days you take away a few minutes from what the sundial reads. And so that compensates for this Earth speeding up and slowing down. We call this the equation of time. That tells you how much you add or subtract in order to make the solar time match. Well, match what? Well, the problem is that clocks don't want to speed up and slow down every day. So rather than having the clock speed up and slow down, we define another time that we call the local mean time. Mean is a math word that means average. So this is the average time. So the sun averages 24 hours a day. So the clocks run at that average speed. And so the actual solar day is a few minutes early or late if you keep track of time that way. And so that means we now have several ways of keeping track of time. We have the mean solar day, we have the actual solar day, and so forth. So when you keep track of time, local solar time is the time according to what the sun tells you the time is. Highest in the sky is noon. Okay. Local mean time is the average, so it's a few minutes off of the solar time, but it runs at a constant speed the entire year. Now, civil time is actually the time the government tells you it is. And that can be local solar time or local mean time, or it's actually something even different. Most of the time, it's actually something slightly different. The government says, oh, this is the time, and so that's the time that you follow. It's often close to one of these other times, but that's the way that works. Now, this is an interesting concept right here, something called the Analyma. And if you look at a really old globe, there's this big figure 8 sort of thing that's sometimes drawn on it. What happens is, if you were to look at the sun like once a week at the exact same time every day and take a photograph, and an amateur astronomer did that and got this photograph right here by sandwiching them all together. And what you would find is that the sun's sometimes to the north, sometimes to the south. Well, instead of making a line here, it's early or late depending on whether the sun's running early or late, depending on whether what part of the orbit Earth is around the sun. And so the Analyma takes into account this. And so in a really old globe, I rarely see it on new globes, but on a really old globe, the Analyma would tell you whether the sun's running early or late and what declination it was at. That turns out to be vital if you're using the sun to navigate by. So in the old times when they used to take sightings of the sun for navigation, then they'd have to know the declination of the sun, but also is it running early or running late.